Thank you so much. Before I share my screen and begin sharing my slides with everyone, I like to begin all of these talks with a brief little bit about myself. I think science is really important, but the people that do science are equally as important. And so if any of you want to reach out to me after this talk, I just want to encourage you all that I'm very receptive and welcome to help anyone that has any questions or wants to further their study or career in quantum information theory. My email is as nhuffman, my first initial and my last name, at alumni.stanford.edu. So feel free to reach out to me after the talk with any questions. I'm Noah. I was born and raised in the United States in a very rural part of the country in Pennsylvania. And I want to thank all of you for being here and listening in English. I wish I was cultured enough to give this talk in Spanish, but there's a famous saying that if you speak three languages, you're a genius. If you speak two, you're average. And if you speak one, you're American. And that definitely holds true for me. So thank you all for being here and enabling me to speak in English. As I have the nice introduction of receiving, I went to Caltech and recently Stanford to study physics. I have a background in experimental physics, but now I do largely coding and a little bit of theory, which I call computational physics. Outside of science, I really love running and telling funny jokes. So yeah, if anyone wants to connect for me on LinkedIn or via email, please feel free to. Okay, so moving right along, let me share my screen here. All right. So my talk today will be on a recent work of mine. You can see my name there in the middle of the screen. It technically isn't published yet. We've just submitted it, but it's on arXiv, and you can look it up. This paper is largely about an experimental system, which I'll show in a slide or two. But my work specifically as the second author on this was on noise learning about this particular system, but the techniques that I'll talk about are broadly applicable. I would like to say for everyone in the room that is a novice in quantum or an undergrad, you're still figuring things out. The work that I have done broadly fits into a category that is professionally known as QVCC, or Quantum Validation Characterization Sciences. And this field is really all about kind of gleaning what errors can occur or are occurring on a quantum computer. So you may have heard of error correction, which is, all right, our qubits are noisy. How do we fix that problem? How do we correct for these errors? Characterization work happens before this. It's basically saying, well, if we knew what errors were happening, what was going wrong, then we would be able to correct for them better, more efficiently, like that. And this is what error characterization is about. How can we learn what errors are even present on quantum hardware? How do we understand what's going wrong in the first place? So that's kind of the general hood under which this work and my work in general fits. And it's a growing field. So if anyone is interested, there should be plenty of opportunities both in research and industry in the near future. So this is the experimental system that this paper was dealing with. I didn't do any of the experimental work. I was collaborating with the experimentalists, so I haven't seen this in the lab. I haven't touched this system, but basically it's a boron vacancy in this nitrogen boron lattice, and so it's kind of these defect qubits, wherein by having one of these vacancies, you have some two energy level system that functions as a qubit. So you may have seen a diagram like this before. This is a quantum circuit with qubits here on the left, and then throughout this circuit, these boxes are gates. And generally, when we think about quantum circuits and errors that can occur, after each of these gates applications, after an H or an S, whatever it is, that can introduce an error. One of these gates can be noisy to execute. However, what was a little unintuitive to me when I first learned about this, what happens in this red box that I've drawn? What happens when a qubit isn't being acted on? If you take a first year quantum computing class, it's kind of just assumed that the qubit is there perfectly waiting, sitting around, not doing anything. And that's a lovely assumption to make, but we live in the real world, and the real world is often non-optimal. And so, to quote Oscar Wilde, it's awfully hard work doing nothing. We think that this qubit should be doing nothing, but actually it's quite difficult to have a qubit doing nothing at all. And this is what's called in the field idling issues. So a qubit is idle when it isn't being acted on by a gate, or a measurement. And it turns out that when a qubit is sitting idle, instead of being in the state that we left it in, it can actually have errors incur over time due to any number of electrical, magnetic issues, neutrino from space, any kind of physical process can cause this qubit to perturb from the state that we initialized it in, even when it's sitting around and doing nothing. So to kind of motivate what this kind of error, these idling issues might look like, I'll mention the block sphere here. Very briefly, if you haven't seen this representation of a qubit, the idea is that, as we're aware from first year quantum mechanics course, this qubit is basically this complex vector. We have this psi naught and psi 1 components, which kind of tell us, okay, we're either in 0 or 1. And this picture looks very two-dimensional, right? Like you just think of this vector in the complex plane, right? But the problem is, these coefficients themselves are complex, right? And so what's one way that we can kind of visualize this, that we can graphically represent a qubit? So we can rewrite this qubit psi as this cosine and sine part of the 0 and 1 vectors, where there's this complex phase between the two. This is an equivalent representation of what I've shown above, and you can see that because if psi naught is this cosine and psi 1 is this sine with the e to the I phi in the front, their complex amplitudes are equal to 1. So this holds. This is an equivalent way of representing a qubit. And given this formalism, we kind of have two parameters here: this theta and this phi. And this phi here just tells us basically the relative phase, the relative complex phase between psi naught and psi 1. But because we have these two parameters, whenever we think about two parameters, like one way of thinking about this is, okay, we have two angles. That tells us something about a sphere. And so from these two angles here, I have this azimuthal angle theta and then the equatorial angle phi. Both of these angles describe this sphere, and then we can now describe this state of the qubit as being somewhere on this sphere. So we have the 0 state at the North Pole, the 1 state at the South Pole, and on the equator here, for example, we have superposition states. And so the idea here is that I will tell you, I will just assert that if we initialize into the 0 state, which is very common for a lot of quantum algorithms, we can employ a pi/2 pulse to get us into a superposition state. And that corresponds to this rotation on the block sphere. And the block sphere, for example, I highlight theta, and then this is where phi is. And so we're going to be particularly interested here in errors in phi, these so-called dephasing errors, since phi is our relative phase between these two coefficients. So we're going to be observing movement here on the equator of block sphere, which is determined by this kind of error in phi. So what's going on and how do we fix it traditionally, these kind of idling errors? So we do this through this process called dynamical decoupling. And what dynamical decoupling is let's say we had some 0, we apply the pi/2 pulse, we initialize in this plus state here, represented on the block sphere by this blue vector. if we left this qubit to idle, we would hope that this blue vector would remain where it is along this axis. But in reality, because of these idling errors, we get some kind of dephasing, which is image B here, where either clockwise or counterclockwise, there's some drift in phi. So phi is going to be changing over time. And the idea of dynamical decoupling is, I mentioned a pi/2 pulse corresponds to a rotation in this plane of the block sphere, but a pi pulse corresponds to a rotation around this plane. And so what we're going to do is we're going to apply a pi pulse after waiting some time. And what this will do is this will flip the vector about this axis running through the center of the block sphere, and then will allow rephasing to occur. And all rephasing is saying, let's wait the exact same time that we've dephased. And if we've done this properly, we'll have arrived back where we began. And so this is the idea of dynamical decoupling. Some things that I want to mention about this to people that aren't familiar with this is that a big assumption here is that the rate of dephasing is constant, that this drift is constant. But what I'll also assert that I hope is intuitive for everyone is that if I do this pi pulsing frequently enough, if I'm pulsing over and over and over again, then approximating this dephasing as some constant drift in time is actually very sensible. It's akin to the tangent line of some function is always linear. If you zoom in close enough on a function, it looks linear, right? That's the idea here, is that even if this drift isn't constant in time, over some very, very short amount of time, it does look constant. And so ideally, with this dynamical decoupling, you'll be pulsing very frequently. And in general, pulse trains that have more pulses will correct for these dephasing errors better. And so here's a GIF of how it looks like. So we have this dephasing followed by this flip about this axis and then rephasing. And regardless of whether that dephasing is clockwise or counterclockwise as distributed by these two different colored arrows, the procedure will work. So, we're entirely agnostic to what direction the dephasing is. This will correct it regardless. And so here's an example of what one of these dynamical decoupling sequences would look like. And so here you see you have this pi/2 pulse, which is going to put us into this superposition state. And then we wait some amount of time, and then we're going to apply a pi pulse. And the reason why this tau, and then there's 2 tau, is mathematical. It's not important right now, but these times are carefully chosen such that after doing this, we pulse, we wait 2 tau, we pulse again, we wait 2 tau, yada, 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 until the end where we wait tau once more, and then we do a pi/2 pulse. And ideally, after we've done all of this, we should be in the state where we began. So this is also just a graphical example of what that would look like. So, in time, we have this kind of pulse train where we're applying some pulses to this, where these are these pi pulses. I'll mention here that kind of important to this picture where I've included this slide is that experimentally, these pulses aren't instantaneous. There's some time over which we institute these pulses, right? And this time between them is this wait time where they're not being enacted. But these pulses are not, in general, instantaneous, super fast pulses. So how can we mathematically describe this dephasing interaction? And the idea is that we have this Hamiltonian here for some spin system where we have this stochastic term, this beta of t. And what we're going to, and this beta of t is, our noise function, basically. It's some stochastic thing caused by some field. And so what we're going to do is we're considering this noisy Hamiltonian, and we're going to involve it with this pulse operator, this P of k, which enacts this e to the I h P of k, where this is the pulse operator. These are going to be pi pulses, right? So this would be a sigma x. And so the qubit will evolve according to this, wherein this unitary, wherein we're evolving under the free evolution given by this Hamiltonian, followed by a pulse, followed by free evolution, followed by a pulse, et cetera, as we continually pulse this. So uh, what that yields here is this coherence function where we're basically just exponentiating this stochastic function with some filter function. And this small f of t is basically this heaviside function that tells us when we're operating under the pulse Hamiltonian versus when we're operating under the free evolution. That's basically all this is saying. So these two heaviside functions are telling us, okay, turn on the pulse Hamiltonian, or no, don't turn on the pulse Hamiltonian. And so this is CFT is this coherence is what we're going to be measuring experimentally. And from this, you can see that it relies on this underlying noise. And so rewriting that equation, so what I've done here is these are both the Fourier transform of b of t and or beta of t and small f of t. So this capital F of t is what's called the filter function, and it has, I'll show you on the next slide, a closed form for any pulse sequence because it's just directly related to this heaviside function that tells us when we're pulsing and when we're not pulsing. So this is just a Fourier transform of that. And then S of omega is the underlying spectral density of the noise. So this is really kind of characterizing what noise is present, what's the noise that's occurring underneath the hood here. And then finally, this C of t is what we're actually measuring experimentally. So if the overlap, the kind of important thing to note here is that if the overlap between this filter function, capital F of n here, and this noise, the spectral density is large, then this coherence is small. And that's bad. We don't want a small coherence. We want very large coherence. And so ideally what we want is the overlap to be small. So we don't want the filter function and the spectral noise to have much overlap with one another. And so it will keep CFT, which is bounded between 0 and 1, but we want it to be 1 as frequently as possible. And so the kind of idea of this, so I mentioned before, we're, kind of naively, we pulse at equal times. And then, by Fourier transforming this, we get this f of n of t. But, if we knew what S of omega was ahead of time, then we could, in theory, design some pulse train such that its Fourier transform had minimal overlap with the spectral noise density and frequency space. So that's the holy grail, the goal. Practically, we don't know S of omega a priori. So we know so in green here, these two things in green are both things that we know. We know this filter function because we get to control the pulse sequence, the dynamical decoupling pulse sequence. And we know what C of t is because we measure this experimentally. But, a priori, we have no real evidence of what S of omega could even be. And so the goal of my work as part of this larger body of work about error learning, right? How do we learn something about what S of omega is so that in the future we can design intelligently these filter functions to maximize CFT? So that's the goal and kind of the problem setup. So what have people been doing in the past in the experimental world? So there's this very powerful and very common delta approximation that people frequently use. So what's going on here is we have this value chi of t, which is just the logarithm of c of t. So it's known from c of t, and it's basically this integral. And this integral here is dependent only on f of n and s of omega, because we're integrating over omega here. And if anyone is curious, this is the closed form expression of f of n like I said, it's just the Fourier transform of this Heaviside function that tells us when we're pulsing and when we're not pulsing. So it has this nice closed form. Well, I suppose it's not nice, but it does exist. It does have a closed form. Um, but the kind of challenge, the practical challenge of doing this for error learning is that um, even if we knew what S of omega was, computing this integral with this closed form for f of n is rather non-trivial numerically, just because f of n can be quite complicated, as I'll show in a slide or two. And so what people do practically is they just say, okay, well, what if we said, f of n divided by this omega squared, so this right-hand side of this integral here, what if this were just a delta function centered at this particular frequency, this n pi over t? And then if this were the case, this integral becomes trivial because we're integrating a delta function, and we can actually just divide basically to get this relationship between the coherence that we measure and the underlying spectral noise density. And this is a pretty, and by the way here, this peak frequency, you'll notice, changes with time, right? So the idea is, well, I fix n, which is my number of pulses. I fix n, and then I can vary time to vary where this delta function is peaked. And then by doing that, I'll actually sweep frequencies. And so I can kind of see the whole frequency spectrum by changing, just letting over time this vary, and I'll see kind of C of t and t, what they do. And so why is this justified? Why can we assume this approximation in the first place? And here's an example. So this is frequency normalized by that omega naught, so this n pi over t. And then this is the filter function for a pulse train of 256, so 256 pulses. And you can see here that, right around one, it's very, very, very highly peaked, right? So this idea of this delta function, this delta approximation is saying that, especially as n gets large, this looks very similar to a delta function. Let's just call it a delta function. Of course, it isn't perfect. I've included this to show that there are these like higher frequency resonances as well. So actually at every interval of 2 here, so at every like odd multiple of this omega naught, there'll be some other peak. So calling it a delta function isn't exactly perfect, but it makes this integral simple to integrate, and so people have done it. So if you want to see too kind of like how this forms, again, here I have divided by omega squared this time. It's not super important here, but we can see that as n increases, this gets closer and closer to a delta function. And so as we basically pulse more frequently, as we include more pulses in this, this filter function approaches this delta function. So this approximation is good when there's a large number of pulses, but it's less good the fewer number of pulses that we have. And I'll motivate this in a few slides, but I'll hint at now. Practically, experimentally, we do have a small-ish number of pulses. The reason being is that implementing each of these pulses, each of these pi pulses is effectively kind of like operating a gate on this qubit and isn't perfect. Whenever we implement one of these pi pulses, we're not perfectly doing a pi pulse. And so the more pi pulses we include in this dynamical decoupling pulse sequence, in theory, that would be good because we'd be correcting this dephasing error better. But because each pi pulse has its own error associated with implementing it, we actually get a lot of error propagation whenever we do a long sequence of these dynamically decoupling pulses. And so practically, we actually live in a regime here where fewer pulses is common experimentally. And so while people have done this delta approximation for simplicity, practically it isn't relevant to the regime that experimentalists are working at today. So how do we kind of work with this? How do we fix this? How do we deal with this? So I'll mention here that it's known that if the total experiment time t is much, much greater than the pulse width, that's what this tau of pi is, um, you can approximate the filter function well with this sinusoidal thing. This is similar to this delta function approximation because when you think about it, this regime is the regime where the width of these pulses is very small, relative to the total time of the experiment. So, or it's as if we're saying they're almost like instantaneous, these pi pulses, even though they aren't. But if we do assume that, we get this very nice relationship of these sinusoidal pulses. And I introduced that because on this slide, I show that approximation in this dotted line, and then the kind of full finite width filter function, the closed form that I showed you earlier. Kind of the similarities and differences between those even, and using those. So, you can see here that especially at these low values of n, there are large differences between these approximations that are in use and actually this closed form, even in the filter function itself. So, here I have this plot of relative L2 norm distance as n increases. And so as n gets very, very large, this approximation actually gets very close to this closed form for this filter function. But in these low kind of, up to 10 pulses, it's actually really quite bad. And so a large part of my work for this paper was actually implementing this in the first place, implementing this finite width filter function. So expanding beyond these approximations that have been in use in the past. And a big challenge of doing this numerically was actually in this closed form. On the right, this term is this sum over n, where n is the number of pulses. And it isn't non-trivial to code this, but it is quite non-trivial to code this and make it fast. And the reason why it needs to be fast is because you'll notice this filter function is a function of both omega and of time. And so what that means is when we do these noise learning experiments, we're integrating over omega. So whatever kind of numerical resolution we want in omega to do this integral, if we have 1,000 points, then this is going to be computed 1,000 times, but for one time, right? And frequently, to do this in experiment, we often have like order of 100 time points. And so actually what ends up happening is the omega resolution that I used that was necessary is like 10 to the 5. And then this is 10 to the 2. So really this function is getting computed like 10 to the 7 times, something very, very large. And so implementing this is non-trivial, but implementing it quickly is actually very, very challenging and was a great deal of effort as part of this work to make this feasible to use in the first place. And so I include here in the bottom right this little plot where I show the execution time for this implementing this finite width filter function. And you should see it increases approximately linearly with n, which makes sense because the real kind of bottleneck here is this sum, which is linear in n. So this is an example of the performances that I was able to achieve. So coded this mostly in Python because that's the system that experimentalists were using. But there are a couple of ways that you can do it natively using NumPy or even vectorizing using NumPy arrays. But the kind of drawbacks of these are that, again, Python is slow and it's native, and this function is called very frequently. And so what I ended up using for everyone's edification, is this package called Numba, which uses just-in-time compiling for Python. So it is effectively as fast at compiling as C should be. C also uses just-in-time compiling. So whenever doing this summation, it should be as fast as possible. And this required like some custom code to define the operations and computing this filter function. But these are all the different ways that you can make this omelet. And here I have shown on the bottom right the numerical differences between these methods, and they're effectively machine precision. So they're all computing the same thing. Right. So now that we understand like what this filter function is and the challenges of computing it, let's talk about doing this integral now. A kind of way that I phrase this, I think, is that if I gave to you S of omega, and then I ask you what C of t was, this is the quote unquote easy direction because f of n is already known. We have this closed form for it. We have some fast way of doing this. And so, we just kind of choose our omega points for the resolution of this integral, and we do this integral, and then we get some value for C of t. What is much more challenging is actually inverting this integral, which is what we want to do. Given some C of t, and again, I know what this f of n is, the question is, what is S of omega? This is much less clear kind of from the onset. I put these in quotations, though, because even this forward direction of computing this integral that I have in green is actually a little bit non-trivial. And so I'll mention this now. So computing the integral in the forward direction is not as easy as you'd like it to be, because this filter function is actually quite spiky. So above on these slides, I kind of had this zoomed out image where there's this huge peak. Well, now I've logged, scaled everything. So that huge peak you can see here is this very first peak where this x is, this filter resonance. And this filter function, as you can see, has several of these peaks, as I showed you before, at odd multiples of this resonant frequency. Excuse me. Or technically they're near these odd multiples, and then what this GIF is showing is actually in time. So as time increases, remember that first resonance is n pi over t. So as time increases, that frequency decreases. So we're basically seeing this whole thing shift to the left. But in general, especially for high n, this filter function gets very, very noisy, or not noisy, but very, very spiky, in that it has very, very sharp kind of features that is shown here on this. And what that leads to is some underlying integrand for this integral that also has very spiky behavior. And this is very numerically challenging to handle because traditional methods like Gaussian quadratures for integrating don't handle this very well. And on top of that, if you use a Riemann sum, which is eventually what we use to solve this problem, you have to be very judicious about choosing what frequency points to sample to take this Riemann sum. If you only sample at these filter resonances, then you overestimate basically this integral drastically, because these resonances are orders of magnitude larger than these other parts. And so your kind of Riemann sum drastically overestimates the integral. But this graph does a bad job of showing it, but these resonances are actually so narrow too that we need quite a bit of sampling in between them as well to be able to evaluate this integral numerically and have it be accurate. And I was using what I found empirically by working with these systems is samplings of around 10 to the 5, 10 to the 6 points, wherein 10 to the 5 points were just uniformly sampled across this frequency range. And then in addition to those, we add additional points around each peak here, basically. So we look at some peak width, we define some peak width, and we add additional points to sample around each of these peaks to capture better the sharp behavior for some fixed number of peaks. And again, about 10 to the 5, between 10 to the 5 and 10 to the 6 total points, we're able to evaluate these Riemann integrals. So now that we know how to do this integral in the forward direction, what about inverting this integral? What about like the a hard way of inverting this, doing it in the reverse direction? I'll go over three kind of potential ways that we came up with to solve this problem. And I'll mention the two in green more than the first, because the first is an idea that we didn't follow up on as much, but I want to mention it because if there are any linear algebra people in attendance, this would be a great future direction actually that I think is wonderful for open work. And I'll briefly overview these on this slide. This first idea of writing some matrix and inverting it is really exciting and powerful because there isn't an ansatz required. So we don't need to have any kind of guess or prior knowledge about what S of omega could look like. We're completely agnostic to that. We just write out these matrix equations and then we invert them. The kind of downside to this is that this matrix inversion is underdetermined. This like system of linear equations is underdetermined, which means that there isn't a unique solution to it. And because of that, it can actually be very difficult to glean something about what this noise actually is. The two other methods that we explored more in depth are using machine learning. This is backed up by prior research. What's really cool about this technique is it's very fast at inference time. So once you've trained your machine learning algorithm, you kind of have these inputs of CFTs that you're measuring, and the machine learning, the neural network is going to output S of omega, what its guess of the noise is. And what's really nice is once you've trained your neural network, when you're in the lab and you measure some CFT, you can kind of throw that into this neural network, and within seconds, it will output, order of seconds, a second or two, it will output an estimate of what the noise looks like. This is very helpful in a setting where you can imagine, you might have some noise that you're worried changes over time, and you're kind of taking measurements as you go and retuning things. And so for like an in situ kind of data streaming scenario, this is very valuable. The downside, the trade-off here with machine learning method is that there's a massive computational overhead. So the training data here is generating these CFT S of omega pairs, and you do that by computing this integral in the forward direction. You just say, okay, here's some synthetic noise. Here's a filter function that you already know. Compute this integral in the forward direction. Here's the corresponding coherence curve. And this is very slow to generate. It takes a long time just because, again, this filter function is getting called many, many times. It needs to get evaluated. It needs to compute this integral. Each kind of instance of like computing a CFT is going to take, a minute maybe at most, depending on the hardware that you have. And so it's very, very cost intensive to generate tens of thousands of kind of CFT S of omega examples. And there's a trade-off here. So you need to generate all of this upfront. And then the machine learning algorithm is also not good at learning things that it hasn't seen. So if you train it, for example, on 1 over F noise, and it gets really good at learning 1 over F noise, if you have a Lorentzian noise profile in the real world and you measure some coherence curve, it isn't going to know that, and it will try to estimate that it's a 1 over F noise profile, which could be very far off from the ground truth. So that's another downside to the machine learning. You still need an ansatz in the sense that you have to model what kind of processes you think the noise could be coming from so that you can generate this training data. So there's an ansatz implicit kind of in this method. And then finally is the method that we decided to use in the paper. It's an optimization-based method that is slower at inference than machine learning. It takes time to do this run this optimization algorithm, but the advantage to it is that no training data is needed. So that's a positive. But both machine learning and optimization rely on having ansatz. So let me just briefly mention this machine learning idea and talk about an issue with it. So as I mentioned, we have this integral kind of relating the noise to what we measure, this coherence curve. And if we do compute this with a Riemann sum, or even we can imagine this being some Riemann sum, we can rewrite it in terms of this Riemann sum, right? So we're going to rewrite it like this. And then if we take that Riemann sum and we break it up, we can actually rewrite it as matrix multiplication. So kind of for each time value that we have here. So this is for one time t. For one time t, we have some sum. Well, for several times t naught through tm minus 1, we have this matrix that we're multiplying by these s of omegas for each, over the frequencies. And then this sum of doing this matrix multiplication is going to be the Riemann sum for each of these times in our CFT vector here. And so the idea is we can just write it out as this. And as I mentioned before, the problem here is that experimentally, we're limited in how many samples we can take of CFT. These coherence times don't last forever, and our measurements are noisy. And so experimentally, the kind of data that we have to work with is like 0^10^1. But to make this Riemann sum work for this integral, because that filter function is so noisy, as I was mentioning, we need like 0^10^5 kind of points. And so what that means is this system of linear equations is underdetermined, and it doesn't have a unique solution. And so what does that look like? Here's an example. So how we would solve this linear system of equations is to use, for example, least norm expectation. And on this plot here, the middle left plot, if you can see my mouse, I've synthetically generated some CFT S of omega profile here. And instead of a CFT is on the bottom here, if you're curious, this is what it looks like. It starts at 1, it decays to 0. The negative logarithm of that, chi of t, which is what is on this left-hand side on this slide, is on the top here. So this is chi of t. And then this is this least norm prediction. And I've specified synthetically some 1/f noise profile. So log scale here, but the form of this noise is like, 1/omega. S of omega equals 1/omega, something like that. And you can see here that by doing this matrix and then inverting it using least norm, we can actually get a result, an estimation of what S of omega should look like that does minimize the norm between the chi of t that it should be and the chi of t that we observe. They're very, very close to each other. The residuals are here on the right. So the residuals are incredibly small, 1 e to the 8. And so this is optimizing for the least norm between the predicted and the original chi of t, which is great. However, you can see here that the prediction that it makes, the prediction of this vector, this S of omega vector, is this like incredibly high frequency, completely non-physical profile. And it's while I'm showing you this blue line here, which is the true underlying, and you're saying, okay, it's oscillating around this. But if this blue line were here, it might be more difficult to say, for example, like what the slope of this blue line was, right, from just seeing this orange. And the problem is that this is because the system is underdetermined. So this orange mess that you're seeing here is like one of many possible solutions. It's the solution that this least norm algorithm found, and it does do a good job of minimizing the norm, but it's providing us this result that's like unphysical. And a strategy of solving this is regularization. So we can add a regularizing term. So basically, it's a penalty term in the optimization. We're saying find a solution that minimizes the least norm with some additional restriction. And so use this Tikhonov regularizer, which is a common regularizer, to reduce this noise in the solution, these high frequency fluctuations. And this is the result of that. You can see here it's much better, but it still has some of these noise issues, and it isn't perfect. It doesn't continue on into this high frequency regime. And if anyone's curious, by the way, why learning is worse here, it's true of machine learning as well. It's just because these values, kind of at high frequencies, they all are very, very close to zero. And so learning is slower in general in this regime. But these are kind of the issues with doing this matrix inversion, is that this system is underdetermined, and it makes kind of these solutions that it outputs, not necessarily follow what you might expect from, something that's physical. So how about this machine learning method? How can we try to learn this noise using machine learning? And again, the idea is, well, let's compute. So we want to compute, given C of t, what is S of omega? The inverse of this integral. So what we're going to try to do is we are going to use many, like I said, classically generated S of omega C of t pairs by doing this integral in the opposite direction, in the easy direction. And then we're going to use this as training data for a neural network. And so this is what the neural network that we used looked like. It was based off of some prior research. And it's a one-dimensional convolutional neural network where we have this one singular 1D filter that slides across this data, where this input layer is a vector of C of t, these coherences measured at different times. And this output layer is S of omega, this in frequency space, this omega. And the idea of this is that this filter is going to capture the time-dependent nature of C of t. We have very good reason to believe, again, because of these kind of continuous curves, that C of t values that are close to each other should be related to one another. And the same is true of S of omega. We don't expect it to be wildly different from one another. We use this, some people may be thinking, oh, if you have time series data, why didn't you use something like an LSTM for network architecture? And the answer is, again, prior research tried this and found that these one-dimensional CNNs work just as well as LSTMs, but have the advantage of fewer hyperparameters. So there's less kind of fine-tuning and training and things like that. They're just easier to work with while being as performant. And so we did this, and we're the first work, to my knowledge, to do this across different numbers of pulses, and then also to consider this finite width. So that's what we did here. I will mention, in case anyone is curious about continuing this work, I wouldn't do this if I were moving forward on doing neural network stuff, because I learned later in this project that these C of t's that experimentalists take are often not at the same times, and these vectors are often not of the same lengths. So for example, for a different number of n, for n equals 1, you might get like 100 C of t samples taken at some number of times, but for n equals 8, you'll get 74 C of t samples that are taken at different times. And the problem with this network architecture is it's fixed length input, fixed length output. So using the CNN structure, it's kind of always expecting like 100 C of t's taken at the same time as inputs. And so it's limiting about this architecture, and it makes it difficult for experimentalists to give you good data. Were I moving forward with this, I think I would try some of these more modern LLM tokenizer kind of neural networks, in that they also handle time data, And there's been some work that shows that like they can learn a CNN. They can do what a CNN can do given enough training data. And so given that these CNNs can work, I figure they can also work. But the big advantage that they have is that they don't need fixed length input. So it could solve this problem of needing, different experimental time samples. So I just wanted to mention that. Um, so how does this noise learning work for synthetic data? So it works very well. Here I show two examples. So this is the neural network's prediction versus like what the true noise spectrum was. So what I did was I generated some true noise spectrum. I generated a C of t with that, and then by doing the integral in the easy direction, and then I fed that C of t back into the neural network that I had trained. And you can see here that in general, especially whenever the kind of parameters of these noise fall well within the parameters of the training sets, this neural network does a great job of predicting what the underlying noise is. So this is the noisy experimental data that one might see. So as I was mentioning before, for kind of different values of n, here's n equals 1 and n equals 8, you can see we get different kind of time point sampling and different kind of number of points as well. The other thing that I'll mention is experimental noise is real. Mathematically, because there's this negative exponential, these coherence curves are, monotonically decreasing. But in the real world, we don't see that. There's noise due to experimental measurements. We can kind of see this overall profile of this noise, but we don't know for certain exactly where that profile is. So what does the delta function look like using this delta function approximation? And basically, there is kind of huge separation in this A parameter. So modeling the noise is just this simple 1 over f noise. Doing the delta function approximation will predict the slope of this correctly across these different ends. So here, this slope is related to this coefficient here of 1. But in general, the kind of predictions that you get by doing this delta approximation for these different ends will vary wildly in what they predict A to be. And remember, this delta approximation is better the higher n is. But in general, if you have these different pulse sequences, especially if you have fewer pulses, you'll get much inaccurate kind of estimates of what this noise could be. And this neural network has improved upon that. So in this image I have here, these CFTs, and then the neural network kind of the backed out, I should say, CFTs that the neural network gives. So on the right, these dotted lines are the predicted S of omegas from using the delta function, and you can see they have this kind of spacing in A. And then these neural network predictions. And you can see the neural network predictions are much closer to one another. They do a much better job of guessing what A is. And then if you take these predicted S of omegas and then regenerate what CFT would look like, that's what these dotted lines, these dashed lines are here on the left. And it just gets noisier as n increases because the underlying experimental data gets noisier as well. And you can see here, as I was mentioning before, at these high frequencies, these neural networks perform worse because, again, at these high frequencies, these CFTs are zero and effectively zero. They're all very small. And so learning takes longer. So this is the same plot as before, but with each of them zoomed out. So you can kind of see where n equals 1, n equals 8, 128, and 512 kind of line up. Okay, so noise learning via optimization. So this is what we end up settling on in the paper that we explore and what we have published. And the idea, and the reason why, by the way, if anyone's curious, is that um, we're running into the issue of this neural network learning method, wherein the training data is very costly to generate. You know, it might take a week or two on like a supercomputing cluster, and as your error model kind of continuously evolves, you um, have to regenerate all of this trained data. And that is very costly to kind of debug and research in a research environment. And so we switched over to this idea simply because we wanted to avoid this really costly computational overhead. And so the idea here, as I mentioned, is that we're basically going to fit some ansatz of our noise S of omega using classical optimization techniques such that the overlap between uh, the measured CFT profiles and the um, derived CFT profiles from this S of omega ansatz are as close as possible. So you can see in this image here, on the top, we have our noisy experimental data and these kind of CFT profiles that result from these optimization procedures that are trying to fit these solid lines to these dotted lines. And here the model is a very simple, you know, one over F fit, where there are actually two parameters here, A and alpha, and alpha is this parameter that corresponds to the exponential on the bottom. And you can see here in this log-log plot, as n increases, as the kind of frequency of these pulses increases, this slope particularly changes. So we saw this using this very simple model, and it led us to believe that something more complicated than just, you know, 1 over f noise is going on here. And so what we do is and this is just showing the difference between this finite width filter function and the delta approximation. So, you know, had we done the same thing using the delta approximation, these dashed lines is what we would have gotten. And the kind of predictions for what these CFT curves would look like are also shown here. And you can see that they're much worse than fully considering the finite width filter function effects. So this is, again, kind of motivation for why we would want to consider the closed form of this filter function in its totality. So what we end up settling on for this ansatz of our noise model is this double power law function. So if you look at this, it can look complicated, but it's pretty simple, I swear. So we have this coefficient here, omega, where omega is some cutoff frequency, such that beyond omega, the behavior of this changes, right? And so you can see here, if omega is really, or I should say, if omega is really small to gamma, I think I misspoke. Gamma is our cutoff frequency. If omega is very small compared to gamma, then this term in the denominator is small, and this whole function looks like this model of 1 over omega noise, where we just have a and omega to the alpha. And so it will behave according to that power law with exponent alpha. However, if omega is much, much greater than gamma, now this term is very, very large. And you can multiply this omega alpha through here, and you'll see that the dominant term here is this omega to the beta term that will make this whole function behave like omega to the beta, 1 over omega to the beta, as frequency increases. So that's the idea here. It's basically taking two power laws and combining them, where this cutoff frequency gamma kind of determines where we're switching. And all of these, alpha, beta, A, and gamma, are parameters for this model. And all we're doing here is simply fitting our CFT to this model by varying these parameters. And so that's what this is showing here. So these, again, these kind of solid lines are these estimates if we only had one power law for these different ends. And then these dashed and dotted lines, respectively, are these estimates for what this spectrum noise density would look like under, I would say, two varying situations. So the first is in kind of considering an average noise profile across n. So as n increases, we probe higher frequencies, but we want, we need some kind of idea for what the noise looks like across everything. We can either use linear averaging or log averaging. So those are this pink and purple line respectively. And then given both of those averaging cases, this fitting that we can do, we can have different choices of loss functions. So using mean squared error, log mean squared error, or relative mean squared error, these are all different kind of loss metrics. You can see the functions that we learn, but regardless of what averaging we choose and what error function we choose, we get very, very similar estimates of these parameters and what this spectrum density should look like. So that's the procedure that we take on. So we show here, what each of these would look like under this 1 over f noise. And then by combining them all and again fitting, we can have this kind of noise that exists over some large span of frequency across all of these different n. And then these are these reconstructed noise profiles from this joint noise. So this is the figure that you'll see in the paper. If you look at, I want to say it's figure 2 or figure 3, but that's how we get there, and that's the work that I did to do it. So if anyone is interested in this work and wants to do noise learning for dynamical decoupling on their own, my GitHub, this package is called FWDD for finite width dynamical decoupling. It's a package that does exactly what I've described. It includes all of this noise learning stuff. And then additionally, it has some of the machine learning included, but it's a little bit less polished since we abandoned it earlier in the project. So you're welcome to check it out. You're welcome. It's like 4 Python files. You can just drag and drop them right into whatever project you're working on. And there are like tutorial notebooks to accompany it. So that's it. Without further ado, that's all I have to speak about today. I hope everyone enjoyed the talk. I see Michael Caracas raised the hand. Oh, what would be, I see Christina ask a question. What would be the best way for me to share these slides?
Hi, good night. I think in Bogota it's afternoon yet. Noah, thank you so much for the presentation. It was really cool. It was really interesting and it was really enlightening. And I just have 2 questions that I would like to make you. It's more in the physical context of the dynamic decoupling problem. Of course, as you say, it's like a good mechanism for reducing noise and reducing like the potential errors that you would get from the system once you are you are dealing with different quantum operators in your system. But of course, there are some quantum algorithms that will require that you somehow leave the quantum system to evolve freely. And in that sense, my question is if maybe applying too fast these kind of mechanisms could affect the system in certain problems, like, for example, the quantum Zeno effect.
Yeah, I mean, as I was mentioning in the talk, you're exactly right that applying this dynamical decoupling too fast is problematic because so in theory it isn't, right? In theory, I would love to pulse as frequently as possible because this kind of drift then I can assume to be constant. And if I'm pulsing frequently, I don't give it much time to move away from its origin. However, in practice, these pulses aren't perfect, right? They're imperfections in implementing one of these on a qubit, and that error stacks as you have more and more of these pulses. So the goal of my work in general, this noise learning, is that if we can learn something about what this noise is, then we can design some pulse sequence to use the fewest number of pulses possible to get the best correction as possible, right? And that depends. So, for example, it's like if I knew how much this drift was occurring over time at different times, I could only pulse whenever like necessary, basically. And that's why I mentioned here, you want to design this filter function such that the overlap with whatever the true spectral density of the noise is very small. And so that's the goal of error learning, right? Is that we're doing these kind of different n pulse sequences because we're in each of those learning something or probing what this noise is because we kind of change what f of n is and we measure the difference in c of t. And by doing that, we're gaining some information about what s of omega is, assuming that it's been constant between our experiments. But by doing this and by doing our procedure, we're claiming that we can learn something about what this S of omega is. And the next step, which my research doesn't cover, but the next step would be how do we, given the knowledge of S of omega, let us design some pulse sequence that looks like this that maybe isn't equally spaced, that has varying spaces in between these pulses such that we minimize the number of pulses while maximizing, what CFT is.
Oh, that's great. That's great. So in that sense, you would also avoid another, let's say, impractical effects like hidden mechanisms depending on the system you would be working with. Okay, perfect. Thank you so
Yeah.
much.
The issue is that like a priori we're like totally agnostic to the system and underlying effects and modeling, as long as there's this dephasing error, T2 error sometimes called, which is very common. We don't know where it comes from, we don't know anything about it, we like know nothing about what this S of omega is. Dynamical decoupling, if these pulses are ideal, should correct for it if we're continuously pulsing all of the time. But again, because of practical difficulties, there are issues there. And so by learning something, again, a priori we're agnostic, but like if we can have some idea of what SMA is, then we can have a pulse train that makes sense for whatever specific process we're working.
That's great. Noah,
Yeah.
thank you so much.
Yeah, this whole idea of equally spaced pulses is like the naive approach. It's just saying that because we don't know anything about what we're dealing with, we'll just equally space these pulses. And also, I suppose it makes this filter function math a little bit easier, perhaps. It makes this thing a little bit nicer to work with. I don't know. I haven't worked with the case where we consider, uneven pulse spacings. But yeah, there's a whole rich kind of future directions to think about different dynamical decoupling pulse sequences. And if anyone's curious to read more, this paper does have a decent like diagram of different pulse sequences. There's many different kinds. There's like this famous CPMG sequence. There's this XY8 pulse sequence. So there's like different pulse sequences that exist out there. And like I said, there's more thought that can be done about how innovative you can get with these pulse sequences. This equal spacing pi pulses is the very simple, naive, I have no clue what's going on under the hood approach.
Is anyone has a more doubt? Yeah. All right. Noah, you can answer it.
Oh yeah, of course. Before I answer the next question, Laura asked a question about. Before I answer it, I wanted to ask you, Oscar. Christina in the chat asked if I could share these slides. What would be the best way for me to do that?
All right. Yeah. She also chat with me in WhatsApp. So if you can share me the presentation through LinkedIn, I will be
Okay.
sending the slides for them.
Yeah, absolutely. All right. Yeah, Laura, you have a question?
Yes. Hi, Noah, and hi, everyone. Thank you so much. I really enjoyed hearing about your work on quantum noise. I think that it's such a fundamental challenge in building reliable quantum systems. For me, noise is the thing that can make information break down, distort calculations, or make results hard to trust. So it was fascinating to hear how you're approaching it. I wanted to ask you, from your perspective, how do you think this research can evolve so that quantum noise doesn't remain a long term obstacle? What directions or strategies do you see emerging to make quantum systems more stable and trustworthy in the future?
Yeah, that's a great question. Anytime anyone asks me this question, my knee-jerk reaction is to say, I mean, build better hardware. You know, I think that's where the most advantage has to be gained, and also right now where we're seeing like the most rapid improvement. You know, earlier this year, Google released this paper where they're like under the error threshold, like their hardware is getting cleaner and to the point where error correction actually makes sense, which is great, you know. And I think that's kind of the been the primary focus of the field, and I agree with the field in that that's where I think there's the most to be gained. So, you know, outside of my work, I think that you know experimental techniques, you know, clever tricks, you know, reducing, you know, different kinds of errors through hardware is the most valuable way to reduce errors overall. Just make the qubits less noisy to begin with. Um, that being said, you know, that's easy for me to say as an experiment or as a computationalist that doesn't do that. And also, I'm sure that there are like limitations to how far we can push that. Right now, it seems like we're making a lot of great progress, but I'm positive that maybe there are some engineering challenges that we can't can't surmount, especially in the near term. So, as far as like my work goes specifically, my work isn't in error correction per se. I'm not dealing with fixing errors. I'm with the step before that, which is, you know, identifying what errors even took place. There's kind of like a co-relationship here where, you know, there are theorists that, you know, you build error models, right? Like you think, oh, like what could possibly be going wrong, right? I mean, we could have crosstalk, we could have leakage errors, you know, whatever. And then there are people like me that, you know, are kind of half in theory, half in experiment that say, well, okay, well, let's go measure the systems that we're working on. And from those measurements, what can we glean about what is happening? And then how can that inform our error models? So, you know, I think my work really slots into um, that kind of niche of like through better identification of what errors are present, we can build for better error correction. As I was mentioning for the last question that was asked, you know, industry standard right now for dynamical decoupling is to do these you know evenly spaced pulse trains, and it is suboptimal. You know, if we did know what the underlying noise was, we could customize these for that noise and achieve better coherence times overall using fewer pulses. So that's kind of what my work enables, you know. I think there's a lot to be improved upon both. As I was mentioning in my slides, for this error classification, you know, learning what errors are present, the holy grail almost is doing this matrix inversion. If there was some way that you could make this linear algebra work out. The big power here is that, like, again, you don't need any assumptions on like what your noise looks like. You don't need any model. You don't need, any bells and whistles. And that's really powerful. So there's still kind of future directions to be explored here. And then same with machine learning. Like I said, trying some, more modern LLM is I think, valuable here. But there's also like work to be done, I think, on the error correction side of things. Given that if you assume that you know something about what this S of omega is, the question of like designing an optimal pulse sequence, is also worth studying and thinking about. So, yeah, I think those are some future directions about my work specifically, but also the field in general. I would say the biggest benefits right now are just qubits that are less noisy, experimental design.
Awesome. Thank you, Noah. I have another question.
Okay.
Building on that, I'm also curious about something from my side. From my side, uh, in computational biology, we deal with complex, noisy data all the time. Do you see any conceptual connections between the way you model or understand noise in quantum systems and the way we handle uncertainty or variability in biological data?
It's a great question. So I'm not a computational biologist. I don't know anything about computational biology, but my answer is definitely yes, because there isn't really anything magical about quantum data. Quantum data is classical data with extra steps. So, for example, on this slide, if you're unfamiliar with a qubit, a qubit is characterized basically by these two complex numbers. But what are two complex numbers but two classical numbers with an I, right? So, or what is a complex number except for two classical numbers with an I? And so, there are ways of thinking about quantum data and processing quantum data that are like entirely classical, and even things like quantum error correction. I'm learning more about it every day, but quantum error correction I used to think was some like magical, mystifying quantum magic, but in actuality, quantum error correction is just classical error correction applied twice. If anyone knows anything about error correction classically, and you have bit flips, a zero can become a one, a one can become a zero. In quantum computing, you have bit flips and phase flips. And the ideas of quantum error correction so far have just been, what if we take classical codes that correct for bit flips and apply them to the bit flips, but also apply them to the phase flips? We just have like two classical codes keeping track of the two different errors. And so, yeah, I think really every way that we handle data in quantum computing and quantum information theory is like very classically inspired and works hand in hand with classical techniques. I'll add an answer to your question that you didn't ask, but there's a lot of overlap in quantum computing and biological problems. Recently, if anyone's curious, I know you're all in Colombia, but here in the United States, the National Institute of Health, the NIH, has like a quantum prize for like quantum applications in biology that I participated in, both on the computing side. So, for example, one big application would be protein folding. We know quantum computing can speed up, but also even in like quantum sensing. So, quantum sensing for, detecting heartbeats or detecting brain activity, things like that. So there's a lot of overlap too in the fields outside of data processing. But to answer your question, yeah, we use classical data processing techniques all the time. I think about data classically frequently and use classical techniques. So yeah, very, very similar.
That's really, really impressive. And actually, I was recently talking with a friend, Michael, that talked before, who's doing his PhD in your topic.
Oh,
We were
wonderful.
talking we were talking about quantum sensing. Yeah. And I was curious about it.
Yeah, yeah. So I mean, I'm not an expert, but I'm definitely aware there are efforts in quantum sensing for like biological applications.
Nice. Really, really impressive. Thank you so
Yeah.
much, Noah.
So there is no more questions. I think that so Noah, really, really thank you, and that
Yeah,
was
thank you.
a really fascinating talk. Even my girlfriend next to me, she's fascinated too. Um, the your talk was truly fascinating, and we all learned about a great deal from your insights and perspectives. For all the participants, we've just shared our WhatsApp channel in the chat, and we will be keeping you updated about upcoming talks, quantum and AI projects, and much more even. And don't forget at 4 p.m., just in half an hour, using this same link, we'll have our next session on quantum error, correction codes, and quantum chemistry. Well, we hope to see you there.
Thank you, everyone. Have a wonderful Friday.
Noah, I have a last question.
Oh, of course.
I know that this isn't an easy field. I think that working on quantum noise is extremely uh, sometimes complex and demanding. So my question is, what drew you to this topic in the first place? What made you want to dive into something so complex?
Sure. It's a great question, and I will rebut the premise and say to everyone that's listening, quantum computing, quantum error correction isn't hard. I know sometimes people like to hype it up to make us look good. Oh, I'm so smart because I do quantum stuff. But yeah, everything in life is doable. Math is math, and if you just join the field and you find someone that is willing to take you under your wing, you'll learn really quickly. You don't even need to know physics as long as you know linear algebra. There's like a lot of things that you can do and really contribute to in the field. So I want to dispel the notion globally that physics is difficult or quantum computing, quantum mechanics is hard. It's really all linear algebra under the hood. So please feel free to explore more. Don't be turned off by people making it sound like magic. It's not. But to answer your question, all right, what got me into? I'll answer two questions. What got me into quantum computing, and then what got me into like specifically quantum error stuff. What got me into quantum computing, I'll be frank with everyone, is I think interest and opportunity. I didn't know what quantum was before sophomore year of college. So this is when I was 20, probably. Had no clue what any of it was or was about. And I took a class in undergrad about quantum mechanics. I was a physicist. I thought it was really cool, and I did well in the class. I enjoyed it, and so I think that sparked my interest. And what I mean by opportunity is I knew at the time, as I know now, that quantum computing was a growing field with a lot of hype. It's adjacent to computing, and it has a lot of potential if it works out to really change the world. And so I knew at the time that I believed at the time that there would be jobs and a career path for me in quantum computing. I'm aware of other physicists in like astronomy or quantum field theory, more esoteric, less economically practical fields that struggle to find work because what they research is so niche, and so you're forced to stay in academia or become a finance bro. And so I kind of liked the idea that there could be a career for me after university in doing quantum computing. So I think that's what got me into it in the first place. What got me into this specifically is, I mean, complete happenstance and I won't say luck, but just environment. I was looking for something to work on. I was looking for a project in grad school, and I happened to get connected with a professor that was interested in doing this and kind of had this idea set up in the first place. And that was really helpful for me. I can give everyone advice that I wish I had, but I think, especially in science, who you are surrounded by is like more important than anything you do in particular. It really, really helps to have good mentors and a team of people that is like has momentum, that is researching something, that is going somewhere. And I think momentum has magnitude and direction. It's a vector. I think in your life, the magnitude of your momentum matters more than your direction. It doesn't really matter what you're doing as long as you're doing something. It's better to do something wrong, quote unquote, than do nothing at all. And so I kind of fell into this work, and it's been popular, so that's been good. But if I could recommend something to everyone here, whether or not you stay in quantum computing or go do something else, really try to find a team of people that you're excited to work with, that's excited to work with you, that will teach you what you need to learn, and guide you and help you out and not leave you out to dry. Research in your fields, who are the famous people, like what are people doing, what are people talking about, and go to them, see what they're doing, ask if you could work with them, and don't stop trying. Just keep at it. So yeah.
Oh, thank you so much, Noah. I really appreciate your answers. Thank you so much.
Yeah, no worries.
So Noah, thank you again, and I'm just finishing inviting you and all the participants for our next talk here in this same link at 4 p.m. in 30 minutes. Quantum error correction codes and quantum chemistry. So thank you so much again.
Yeah, thank you.
We will be talking on LinkedIn.
I'll take my slides.
All right, all right. I'll send the slides to the people, and thank you so much.
All right, bye.
Thank you to all people. Goodbye, and remember 4 p.m. here in the same link.